Welcome to lecture number 21 of my series PH4105 Advanced Mathematical Physics. Here, at present, we are discussing differential geometry, and in the last lecture we had met a very important player in the subject, a 0k tensor or a covariant tensor of rank k at a point P. And we had defined this basically as a multilinear map, which will take k tangent vectors at the point P and return a real number in a multilinear fashion. And this is an obvious generalization of the notion of a covector, which we have studied before, and according to that, a covector is nothing but a 0-1 tensor. We had also learned how to define a linear combination of tensors at a point P and defined ATP plus BSP, where A and B are real numbers and TP and SP are 0k tensors at the point P respectively, as something, again a multilinear map, which takes in k vector fields as arguments and returns the linear combinations of A times TP acting on these same vectors plus B times SP acting on the same tangent vectors. We had also defined the tensor product TP cross SP of a 0k and a 0L tensor, which is a 0k plus L tensor. So takes k plus L tangent vectors as arguments, V1P all the way through Vk plus L at P, and this gives us the number which is TP acting on the first k arguments of this set and SP acting on the last L of them. It is easy to prove that this yields a k plus L tensor at the point P. Finally, we had also talked about what happens when we use coordinate systems on a manifold. So if you are using a particular chart where x1, x2 up to xn are coordinate functions, then TP can be written down as a linear combination of the tensor products dxi1p, dxi2p up to dxikp of the differentials of the coordinate functions, where the coefficients TP, I1, I2, Ik are defined to be the result of TP acting on the coordinate basis vector fields del xi1p, del xi2p up to del xikp. With this background, we are going to take things to the next level today and talk about tensor fields. We had earlier learned about vector fields. These were extensions of the notions of tangent vectors at a point, and the idea basically was the following. To each point P of the manifold, or at least to each point P in a region of the manifold, a vector field would assign a vector at that point P. This idea is easily extended to the notion of tensors, and we can extend the idea of a 0k tensor at a point P to get to a 0k tensor field in exactly similar fashion. A 0k tensor field T on a manifold M is a map that assigns to each point P belonging to M a 0k tensor at P. Note that it not only assigns a tensor to each point, that tensor is tied to that point. This is of course exactly what happened in the case of vector fields. Of course, we have described this tensor field here as something which is defined all over the manifold M, but it might very well be a situation where it's defined only over a part of M and not over the entire thing. And then the definition here would have to be modified somewhat. Now, given a 0k tensor field, you can actually also think of that as a map which takes in k vector fields, x1, x2 up to xk, and returns a function denoted by t acting on x1 up to xk. Now, how do you define this function? That's pretty straightforward. A function, of course, is something which returns a number at each point P of the manifold. So what we need to do to define this is, of course, specify exactly what the value of this quantity T of x1, x2, xk is at a point P, and the definition that we use here is the standard obvious definition. T acting on x1, x2, xk gives us a function whose value at the point P is given by the result of the tensor Tp, which is the value of T at the point P, acting on the values of each one of these vector fields at the point P, which are of course k tangent vectors at the point P. Remember, a tensor, in particular a 0k tensor at a point P, acts on k different tangent vectors at the point P and returns a number. And that number is nothing but the value of this function T of x1, x2, xk at the point P. Now, a special kind of tensor field is one that we will focus on, something called a differentiable tensor field. And there, the idea is very simple. If given smooth vector fields x1, x2, xk belonging to factor x of m, the set of all smooth vector fields, the result of T acting on x1, x2, xk is always a smooth or C infinity function, a member of C infinity M, then we say that the tensor field T is a differentiable or smooth tensor field. Now an important special case arises when we have a coordinate system defined on a manifold. Then we have coordinate functions assigned to each chart, and along with these coordinate functions you get tangent vectors which are defined through the coordinates del x1, del x2 and to del xn. Now if you were to feed the tensor T these vector fields del xi1, del xi2 up to del xik as arguments, you are going to get a function which we are going to call ti1 dot ik. This is a component function of the 0k tensor field. And using these component functions, you can easily figure out what the resulting function will be when T acts on any bunch of vector fields. Note that x1 through xk, these are all vector fields, and they can all be expanded in terms of the local basis provided by the del xi's. So x1 can be written down as x1i1 del xi1, x2 can be written down as x2i2 del xi2. Similarly, xk can be written down as xkik del xik. Now, given the fact that the tensor T is actually a linear map, it follows automatically that the tensorial field T has the same linearity property. Indeed, it's not just R linear, it's actually C infinity linear. We will prove this rather obvious result in a while. So what you get here is T acting on del xi1 up through del xik times x1i1, x2i2 all the way up to xkik. And this, given the definition of the components of T, can be simply written down in the form ti1 ik times x1i1 xkik. Now, it's obvious from this result that a 0k tensor field is differentiable, that is, T acting on every smooth bunch of vector fields will give you a smooth function if and only if these components, which are n to the power k in number, each index here, each of the k indices can take n distinct values. Each of these components must be smooth functions. If they are all smooth functions, then the 0k tensor field is a differentiable tensor field. I will now state a few definitions which are relevant for tensor fields. Now, if these definitions seem to be something that you already have seen before, there is really no cause for surprise there. After all, each and every one of these definitions and some of the results that we will prove henceforth will be very closely modeled on results that we know for tensors. So, it's understandable if many of these results seem to be sort of already known to you. However, note that the context is different, and I'm pretty sure you will understand what I mean when I start stating the definition. So let's begin. If T and S are both 0k tensor fields and A and B are real numbers, we can define their linear combination AT plus BS, which will also be another 0k tensor field, by the following basic rule. AT plus BS at the point P is defined to be A times TP plus B times SP. Note that we already know how to linearly combine tensors at a point P, and we are just using that to define a linear combination with real number coefficients of tensor fields. Now, the fact that this is a tensor field is sort of obvious because at every point P, it defines a tensor at point P. Of course, that this is a tensor at point P is something that we had already established before in the previous lecture. What is not absolutely trivial but is still quite simple is the proof that if T and S are both smooth tensor fields, then AT plus BS is also going to be a smooth tensor field. Now, for another definition, if you have a 0k tensor field T and a function f on M, we define the product ft, the product of a function f and the tensor field T, as a 0k tensor field whose value at the point P is defined via the obvious definition. F yields a number f of P at the point P, and if you multiply the value of the tensor field T at the point P, Tp, by that, you get another tensor at this point P. And this is exactly how you define Ft. A tensor field whose value at the point P is given by f of P times Tp. Once again, a slightly non-trivial thing would be to prove that if f is a smooth function and T is a smooth tensor field, so is Ft. But again, the proof is really rather simple. Now, for one more definition, that of a tensor product of tensor fields. Now, when we were linearly combining two tensor fields, both had to have exactly the same rank. They had to be both 0k tensor fields. On the other hand, when you're talking of tensor products, you can take a tensor product of a 0k tensor field T with a 0L tensor field S, and the resulting thing, the tensor product T cross S, is going to be a 0k plus L tensor field. So, a covariant tensor field of rank k plus L in the old language. And its definition is exactly what you would expect. T cross S, this tensor product field at the point P, is defined to be the tensor product of Tp, the tensor which you get when you apply the argument P to the tensor T, tensor product with Sp. Now, let me remind you that Tp, the value of T at P, can always be written in this form. This is something we had established in the last lecture. If you apply Tp, the tensor at the point P, to the coordinate basis vectors del xi1, del xi2, and del xik, each at the point P, you get a number. Of course, you get n to the k numbers. You take this particular linear combination of the tensor products of the dxi1p with dxikp with these coefficients, that actually is the same as t. We had already established this in the last lecture. Now, this quantity here, Tp acting on del xi1p, del xi2p, all the way up to del xikp, is nothing but the tensor field T acting on del xi1, del xik, the coordinate basis vector fields. This whole thing, of course, is a function whose value at the point P is given by this quantity. So what you have is this expression. This function at the point P, that's nothing but this coefficient here, multiplied by dxi1p, tensor product with dxi2p, tensor product with dxi3p, all the way up to dxikp. Of course, when I say multiplied, I really mean contracted, because it's not only multiplied, you are also going to sum over all these repeated indices. But by the definition of a function multiplying a tensor field, we see this is nothing but the function t acting on the vector fields del xi1 through del xik multiplying the tensor product of dxi1, dxik. So I am actually using both the definition of the tensor product and the definition of a function multiplying a tensor here. This whole thing evaluated at the point. Since this is true for all points P where the coordinate system can be applied, that is, all points P within the domain of the chart u, phi, whose coordinate functions are given by this, you can write, at least within that particular coordinate system, T is always given by this function or bunch of functions, component functions here, times the tensor product of dxi1, dxi2 up to dxik. This is a result which is rather trivial if you think about it, but will come in very, very greatly handy in the long run. With the definitions out of the way, we will now state and prove some important results. The proofs may sort of invoke a bit of deja vu in you, because many of these results would be very similar to what we have already done with individual tensors, and these are almost direct extensions to tensor fields. The first result, however, is something which establishes something we had already talked about a while ago. The fact that a tensor field is not only linear in its arguments, it's actually C infinity multilinear. To see that, what we need to do is take a look at this setup. T is a 0k tensor field on the manifold M, x1 to xk are vector fields on M, and f is a function on M. So what we have done here is given T the arguments x1 through xk, but I have multiplied the ith argument xi by f. And we are looking at this resulting function, and in order to figure out what this function is, we are going to, of course, evaluate it at a particular point P. Now, by definition, this is going to be Tp acting on the values which these arguments, these vector fields take at the point P. So, x1 will be replaced by x1p, x2 will be replaced by x2p, and so on, all the way down to xkp. And the important thing is xi here, which has been multiplied by the function f, will be replaced by function of f at the point P, this number, multiplied by xip. So, Tp, a tensor of rank 0, k, which we already know is a multilinear map, has been given an argument where the ith vector has been multiplied by a number f of p. And of course, according to the definition or basic property of a tensor, what you're going to get here is f of p, the number, times Tp acting on x1p, x2p up to xkp, with xip staying just xip here, the fp having come out. And that is by definition of a multiplication of a function by a tensor, the same as f of t with arguments x1 through xk at the point P. Note that this expression f of t x1 through xk at the point P is by definition f of p times t x1 through xk at the point P, and that exactly is this times the f of p. And since this is valid for all p at which the tensor t is defined, could be the entire manifold, what we end up with is this result that the function you get when t acts on x1, x2, xk with xi, the ith argument here multiplied by the function f, is the same as the function f multiplying t with just x1, x2, xi, xk as arguments. So, putting in a function times a vector field as one of the arguments multiplies the resulting function that you get by the function that you're multiplying the vector field by. This is what C infinity linearity means. In other words, you can just pull out a function f from the bunch of arguments outside. Now, you also have this very familiar result, which is actually quite trivial once you look at it this way. If you take T, the tensor field, and give it the arguments xi through xk, but replace the ith argument by the sum of two vector fields xi plus x prime I, and evaluate the resulting function here at the point P, that by the definition is Tp, acting on all these vector fields at the point P, which in particular means that the sum here, xi plus xi prime, becomes xip plus x prime ip, and by the linearity of a tensor at a point P, this breaks up into a sum of terms like these, which can then be rewritten rather easily as t acting on x1 through xk, acting on the point P, plus t acting on x1, x2, x prime I through xk at the point P, which is just the definition of t acting on a bunch of vector fields. And then by using the definition of the sum of two vector fields, we just get this result. Again, this is valid for all p. So the upshot is, if you replace any argument by the sum of two vector fields, you get the corresponding sum of the resulting functions. This is what you mean when you say that a tensor field is a C infinity multilinear operation if you replace any of its arguments by a linear combination, and here the linear combination could be linear combination with functions and not just numbers. What you are going to get as a result is the same linear combination of the individual results. This is something which is trivial for linear combinations which involves numbers, but for tensor fields it also works when the multiplying factors are functions rather than numbers. Now the converse of this result gives us an alternative way of defining or talking about a tensor field. We have already defined a tensor field as a map which maps every point P on the manifold to a 0k tensor defined at that point. But alternatively, we could also talk about T as a map which takes k vector fields to a function on M, with the additional property that for any functions f and g which are real valued functions on the manifold, note that we are not making any statement about the smoothness of f and g here. In particular, we have not demanded that they are C infinity functions. For any two such functions, if you give T this bunch of arguments x1, x2 up to xk, with the ith argument replaced by f times xi plus g times x prime I. The function f times the vector field xi plus the function g times the vector field x prime I. The result is the following. The function f times t acting on this bunch of vector fields with xi in the ith position plus g times t acting on the same bunch of vector fields except that the ith position is now taken by x prime I. If this happens, then T actually represents a 0k tensor field. It's actually pretty trivial to prove this. All that you have to do is essentially show that the demand that Tp acting on x1p through xkp provides a multilinear map from k tangent vectors to a real number are equivalent statements. Using the C-infinity multilinearity, we have already proven that a tensor T can be written down in this following form: Ti1, I2, Ik, a bunch of n to the k coefficient functions times dxi1, direct product with dxi2, tensor product with dxi3, and so on, all the way up to dxik. Now this is exactly what we had proven a while ago, so let me not repeat the proof all over again. But let me just compare this with what you already know about one-forms. One-form alpha is written down in the form alpha I dxi, which is also the same as alpha acting on del del xi. That's what alpha I is, dxi. It's obvious that a T here essentially is a generalization of this one form to a higher order thing where you have, instead of a single dxi, tensor products of a bunch of dxi's, k dxi's to be precise. In contrast, capital X vector fields, we have already seen that they can be written down in the form capital Xi times del del xi, where capital Xi is nothing but the vector field x acting on the coordinate function small xi. So capital X is capital X acting on small xi del del xi. Just like alpha, a one form, is alpha acting on del del xi dxi. The difference, of course, is that one forms act on vector fields to produce the coefficient functions, whereas vector fields act on coordinate functions to produce the coefficient functions. Now, from the definition, it's obvious that one forms are really nothing but 0, 1 tensor fields, and the tensor field T that we are looking at now, the 0k tensor fields, are essential generalizations of one forms. We could of course also have generalized vector fields to higher orders, and that's exactly what will give us k0 rank tensors, or in the old language, contravariant tensors of rank k. But we are going to talk about that in a later lecture. Now the final thing that we are going to do today will again be reminiscent of what we did with 0k tensors. We are going to talk about the change of coordinates, but this time the effect of a change of coordinates on a tensor field. Let me remind you that a change of coordinate essentially occurs when we have two different charts whose domains have an overlap. So within that overlap region, you could use either the chart whose coordinate functions are x1, x2 up to xn, or an alternative chart whose coordinate functions are x prime 1, x prime 2 up to x prime n. Now, this tensor T, in terms of these new coordinates, will have a bunch of components, which are nothing but the tensor T acting on del del x prime I1, del del x prime I2, and so on. But remember, T, this tensor, is nothing but T j1, j2, jn times dx j1, tensor product dx j2, tensor product dx jn. And this whole thing has to act on this bunch of vector fields. Now, by definition of a tensor product of a bunch of one forms, this is really nothing but dx j1 acting on the first argument del del x prime I1 times dx j2 acting on the second argument all the way down to dx jn acting on the nth argument. And these quantities dx j1 acting on del x prime I1 are exactly what we mean when we define these coefficients. Del x ji, del x prime I1 is a shorthand for just this quantity. Now you have to realize that what is really going on here is something more complicated, because it's not really the x's which are differentiated with respect to the x primes. After all, x primes are functions on the manifold, so are x's. X is not a direct function of x prime. But let me remind you that what we do here is we define this via proxy functions. And since whenever we talk of change of coordinates, we actually use those proxy functions to talk about these change. So in most cases, this looks very much like an ordinary partial derivative. The upshot of all this is the very, very famous change of coordinates rule for tensor fields. T prime I1 I2 dot In is del x j1 del x prime I1 del x j2 del x prime I2 dot 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 del x jn del x prime In t j1 j2 jn. So once you change your coordinate system, the component functions of a tensor field are linear combinations, actually C-infinity linear combinations, because all these coefficients are products of functions and hence functions themselves of the components in the original coordinate system. And the coefficients here are given essentially by n copies, if you're talking of a 0n tensor, of the coefficients that you use for transforming one forms. This again emphasizes the notion that a 0n tensor is nothing but a higher order generalization of a one form. I have just realized that I have committed a cardinal sin here of mixing up my notation. I have used the letter n in two different senses here. One, when I originally talked about x1, x2, xn, there n was a dimensionality of the underlying manifold. And just a while later, I have talked about an 0n tensor. I really meant to talk about a 0k tensor, as I have been doing in the rest of the lecture. Once again, let me contrast this with the cases we already know. For vector field components, x prime I is given by del x prime I del xj dxj. This so-called partial derivative, which are actually partial derivatives of proxy functions, is different from the partial derivative sitting here. The covector fields or one forms actually transform in this manner. Alpha prime I is del xj del x prime I alpha j. As I have already mentioned, this transformation rule emphasizes the fact that this is nothing but a higher order generalization of a one form. Let me also remind you that a similar transformation law works for tensors at a point P, but the major difference there, and this is actually going to be quite an important difference, is that in the case of tensors, the combination coefficients involves products of numbers del x j1, del x prime I1 at P and so on, rather than functions. And this fact becomes very important when we talk about doing calculus with tensor fields, something we are going to talk about much later. Now we have essentially talked about 0k tensors so far and 0k tensor fields. Now it's rather obvious that if 0k tensor fields are there should be k0 tensor fields as well, or even kl tensor fields. And these are of course very important objects, things which we used to call contravariant tensors of rank k and mixed tensors of rank k, l respectively in earlier notation. This is something which we still often call them today, and they are of great importance in various physics applications. We are going to talk about these in the next lecture. The only trouble with this is that whatever I am going to say will be so similar to what I have said about 0k tensors and 0k tensor fields in this and the previous lecture, that the whole thing might end up being rather boring, both for you the listener and me who has to keep on saying something very similar over and over again. But again, these definitions and results are going to be very, very important for more interesting things that are going to come in the future, so we have to go through with them. In the next lecture, I will just go through these issues a bit more rapidly than I have done so far, perhaps omitting some of the details, because if you have understood the results for 0k tensors and 0k tensor fields, the corresponding results for k0 or kl tensors and tensor fields are very, very similar to work out. Anyway, bye till the next lecture.